In this video, we're going to go over multiple regression. And specifically in this video, we're going to talk about when we have quantitative predictors. When there are categorical predictors, there's a little bit more that we have to think about. And so we're going to save that for your next statistics course. So while simple linear regression uses one independent variable to predict the outcome variable, multiple linear regression actually uses any number of predictors or any number of independent variables to predict the outcome. So the difference between simple linear regression and multiple linear regression is that we can have multiple predictors with multiple linear regression, which means our model equation is a little bit more complicated. If we can remember the model equation for the simple linear regression where we had y prime equals a plus bx, we still have that same type of setup or that same form in the equation, but we're just going to be adding terms for each predictor. So our model still has that intercept term, that a is the y-intercept. That's the value of y when all of the x of i's, all of the predictors are equal to 0. And then we start adding terms that have our slope multiplied by our predictor. So we have b sub 1 times x sub 1. So that's the slope for the variable or predictor x sub 1. And since we have multiple of these terms, we are using an index here, and that index is going to end at the number of predictors, which I'm using as k in this equation. So there's the slope times the second predictor plus the slope times the third predictor, so on and so forth until we get to the slope times the kth predictor. All of those b sub i's, b sub 1, b sub 2, b sub 3, so on and so forth, they are all slopes on their specific predictor. And so one of the difference in interpreting our slope now is that the slope actually represents the amount by which y changes when that specific predictor increases by 1 while holding all of the other predictors constant. And so we want to see the effect of that specific predictor. That is what that slope. So that is what that slope represents. And so all of the other predictors are held constant. All right. The assumptions to the ANOVA model, I did write and I wanted to point out in this slide here is that this is just an introduction. And so there are multiple model diagnostics that we go through with multiple regression, since it is a very flexible and widely used statistical method. And so we're going to touch the surface with these assumptions, but you will learn more assumptions in your next statistics class, EDRM 705. But I am going to go over all of the assumptions, but you will learn more methods for checking these assumptions. And so it may be a little uncomfortable here, but here we go. One of the assumptions is that we need linearity, right? We use the term multiple linear regression. That means that we have to have that relationship between our predictors and the outcome. It must be linear. One way to check that assumption is to do a graph, a scatter plot, where the vertical axis has the residuals and the horizontal axis has the fitted values. These are the predicted values here. This is a graph from R, the statistical program R, and R says predicted values, fitted values instead of predicted values. JASP, which we're using, uses predicted values. But when we see a plot of the residuals against those predicted values, we just want to see random scatter. If we see random scatter, which we see in this picture here, then that's evidence that we have satisfied the linearity assumption. The next assumption is independence of errors. The residuals should be independent of each other. If they're not independent of each other, then that means that that we may be missing some important variable, or there may be some other issues with our actual model. And so to check this assumption, we're going to use this same exact graph here, the residuals versus the predicted values. And we don't want to see any patterns or clusters in the residuals. If we do see patterns or clusters where a bunch of the points are kind of clustered together, or there's some pattern in that picture, that might mean that there's some other variables that we're missing out in our study that may be very important to be included, and we're missing it. Homoscedasticity, we talked about this when we were looking at the two-way ANOVA. I said, oh, we want homogeneity of variance. Well, this is a very similar concept. We want the variance of the residuals to be constant across all of the values of the predicted values. So we're going to also use the same exact graph here, and we want to see that the spread, and when I say spread, I mean like the vertical spread of our points in our scatter plot here is pretty constant. So we need consistent spread in this residual plot. Now, I've shown you a graph where most of those, where these assumptions are satisfied. Now, I see that there is a point that's out here that's off to the side. But since this is a pretty large sample size here, sometimes you can have some of those 1 or 2 points that are pretty off, or away from the general scatter in the scatter plot, and that's fine. What we want to look at is for any substantial deviations from that random scatter, right? And so I want to show you some pictures that you can look out for that would show evidence that at least one of these assumptions may not be satisfied. What's traditionally taught is that we may see a fan-shaped graph or a U-shaped graph. It may be upside down U. If there's trends in that residual versus predicted values scatter plot, that's evidence that these assumptions are violated. And so I have a couple of graphs here. For instance, here, probably in algebra, you didn't think about anything being fan-shaped because it wouldn't be a function in algebra. But anyway, a fan-shaped graph. This is an example of a fan-shaped graph. Notice how this plot starts out very low variance, meaning the points are not very wide spread out vertically. But as we continue to go to the right, the vertical spread in these residuals gets larger and larger. That is a fan shape, and that's evidence that some of these assumptions are not satisfied. For instance, homoscedasticity. In this example, this is another example where these assumptions may not be satisfied because we get an upside down U shape here, meaning the residuals for lower values for lower predicted values are mainly over here and over here on the low side. But for the middle range of these values here, our scatter or our residuals are in this area here. So we clearly see a pattern in this scatter plot here. Also, the homoscedasticity or the constant spread of the residuals is not seen in a graph like this, right? And so this is another example of a graph where I'm worried about at least one of these three assumptions. This is another one. This one's a little harder to see, but there are look at this gap in this area right here. There are no residuals in this area here, whereas all over on this side of the graph, we see residuals in this area, right? And so there's something missing in this that deters this from being a completely random scatter. And so this will provide also evidence against at least one of these three assumptions. And so if we see random scatter, we're good to go. We have evidence that these three assumptions are met. If we see any of the other patterns or some weird spaces or gaps in a scatter plot or in the scatter plot, then that might be some evidence that at least one of those assumptions is not met. So those are three assumptions, and we're going to use this one graph to look at those three. Now we're going to look at another graph to check this next assumption, which is the normality of the residuals. The residuals should be normally distributed. And so we're going to look at a QQ plot. And as we've always done with QQ plots, if we see a nonlinear pattern or multiple points that are deviating from that diagonal line that's in the QQ plot, then that's evidence that that assumption has been violated. We need this assumption because we're going to use some t-tests and some f-tests. And so this is an example of a normal QQ plot that is where the assumption is satisfied. You know, if I look here, these points are kind of veering off at the end. this single point here is away from the line compared to those other points. But again, our sample size is pretty big here, and seeing one point that's not terribly far, but it's noticeably far from the line compared to those other points. This is still a graph where I say that the assumption of normality of residuals is satisfied. Another example where this assumption is not satisfied is an example like this. Notice these middle points are close to that diagonal line. I'm not sure if you can really see it in the screen there, but we have a diagonal line, and so we would hope that most of our points are on that line to satisfy the assumption. But if you look, first of all, this is a curved pattern in this scatter plot, and then a lot of these points are kind of deviating away from the line. This is very strong evidence that we have extreme skew in our residuals. And so this will be a violation of that assumption. And then the last assumption is that there is no multicollinearity. Collinearity just means that our predictors are correlated. They're related to one another. So going back to the original predictors in the model, we don't like for those things to be correlated because they inflate the variances, which messes up our standard errors and our hypothesis tests, our confidence intervals that we could construct based off of the analyses for multiple regression. And so we don't want any multicollinearity. We don't want the predictors to be related to one another. So we can check this multiple ways. This semester in this course, we're going to check it one way by calculating the variance inflation factor, or the VIF. It is a calculation based off of how much the variances are inflated. And this assumption is satisfied as long as that VIF, or that VIF, is less than 10. As long as it's less than 10. We have a violation of this assumption if it is greater than 10. So these are all of the assumptions for our multiple linear regression, but these are the ways that we're going to walk through checking those assumptions. And as you'll see in your next statistics course, you will expand on the methods for checking these solutions or assumptions. Now, in addition to checking the assumptions, there are some choices that we can make based off of building these models. So multiple linear regression analysis can be thought of as a model building process, because we have some predictors that we think may be related to that predictor, but we don't know if it's a significant predictor, right? And so we're basically building models, and there are several different ways that we can build those models. I'm just going to talk about two, and in our actual course or for our assignments, we're only going to use one method. One popular method is to use stepwise regression. Stepwise regression starts with no predictor in the model and step by step adds predictors one at a time based on significance. And so they'll start with an empty model, add a predictor. If it is significant, meaning if the p-value is less than or equal to alpha, which is usually 5% or 0.05, then we will keep that variable in the model. If it is not significant, that means the p-value is greater than 5% or 0.05, we'll remove it, throw it away, and then try the next predictor. And then we'll continue this process until we've gone through all of the predictors and only the significant predictors are in my final model. That is stepwise regression, starting with 0 and ending with only the predicted ones, or the significant predictors, sorry. Backward elimination, this is the method that we're going to use. What we're going to do is we're going to throw the entire set of predictors into that model equation, all right? And then we're going to step by step, and I probably shouldn't use step by step, but we're going to basically eliminate any predictors that are not significant, starting with the most insignificant predictor. So start with the entire set. And then I'll remove the predictor with the largest p-value that's greater than 5%. All right? And I'm going to do that one at a time. until I'm only left with a model where I only have significant predictors, p-values less than 0.05. All right, and so we're going to use the backward elimination method. There are some other methods. Even JASP can handle some additional methods, but we're just going to focus on the backward elimination. And then when you get in your next statistics course, you're going to talk about some of the other methods. I just want to point out some things to remember in JASP. Well, first of all, in general, we're restricting all of our data analysis in this course regarding multiple regression only to quantitative predictors. All right. Categorical predictors require a little more thought and coding and things of that nature. And that's going to be the topic, one of the first or second topics that you're going to cover in your next statistics course. In JASP, when you're entering your model, you're going to place your outcome variable, the thing that you're predicting, into the dependent variable box. You're going to select the backward elimination method, and then you're going to put your predictors into the covariates box. Sometimes people call predictors covariates. Another thing that is easy to forget, and sometimes I even forget this, but we have to change the p-value for removal in the backward elimination method in JASP to 0.05 if our alpha is 0.05. And that's in the method specification section. I'll show you all of this in just a second. And then we're going to, for the assumptions, we're going to select the tolerance and VIF in the statistics section. We're going to do the residuals versus predicted in the plots section. And then we're going to get our QQ plot of our standardized residuals that's also in the plots section. And so let's go to this example here. It says a community development social worker is investigating factors that may significantly predict heating costs. A random sample of 20 homes was selected and data were collected on the following variables: mean outside temperature, which is measured in degrees Fahrenheit, number of inches of insulation in the attic, age of the furnace, that's given in years, and heating cost in the month of January, that's given in dollars. The goal is to determine which of these factors significantly predict heating costs at the 5% significance level. And so first, I know I have 4 variables here. And our goal is to determine which of these factors significantly predict heating cost. That means my predicted variable is going to be heating cost. And so they ask, what are my predictors? It's going to be these first 3 variables here: temperature, number of inches of insulation, and age. Those are my predictors. Now what we're going to do is we're going to go to JASP. We're going to run the model using backward elimination. And then we're going to obtain the model diagnostics. So some people call looking at the model assumptions conducting model diagnostics, seeing if this model satisfies all of those assumptions. And so I'm going to go to JASP here. And here is my data. Notice here I have cost, temp for temperature, insole for insulation, age, that's the number of years of age of that furnace. And then I have a variable here called garage. That is a yes or no or 0 1 variable. It is categorical. And so I'm not including that here. And so I'm going to ignore that. So I'm going to use these 3 as my predictors or my covariates. And this is my dependent variable. So I'm going to go over here to regression, go to linear regression, and I'm going to put cost as my dependent variable. Next, I'm going to select my method, which is backward. And then I'm going to have my temp, insole, and age as my covariates here. All right. Now, I've gotten just these 3 tables so far. Just so that you'll know, and we're going to look at these tables more specifically. Remember, backward elimination starts with all of your variables in your model, and then it removes any that are insignificant until it ends up with a model that only has significant predictors. This M sub 0 and M sub 1, this is how JASP is telling us the number of models we're running, right? So since I have two of these values here, there are two models, model 0 and model 1, right? If you want to quickly see which variables are significant or create your model equation, you're going to go to this coefficients table here. Notice model 0 or M sub 0 has an intercept term, temperature, insolation, and the age variable, right? And remember that age variable was insignificant. One of the things that I already forgot was to go here to model method specification, right? Remember I said that we need to ensure that we're using 0.05. Well, if I go to this menu at method specification, I'm going to change this to 0.05. So this is the p-value that I'm going to use to remove any insignificant predictors. And so notice this was 0.032. It was in this first model. It's greater than 0.05, means it's insignificant. I need to remove this in my second model. And as you can see, my second model information starts at this line. It only includes the predictors, temperature, and insolation, right? And notice all of those p-values, or both of those p-values for those predictors, are less than 0.05. They're significant. All right, but I have two iterations that my model went through, right? What we're doing first, though, is we're getting our model diagnostics, checking the assumptions. And so one of the model diagnostics is in this statistics menu here. I'm going to open that menu. And over here under the coefficients section, there's a tolerance and VIF. And so I'm going to check that. And it adds two columns, tolerance and VIF. You'll talk about tolerance in another course. And then under this plot section here, I'm going to get the residuals versus the predicted and the QQ plot of the standardized residuals. And they should appear shortly. Here is our data. And so I'm going to go back to the notes. I've copied and pasted this into our notes. And so we'll first look at checking the linearity, independence of errors, and homoscedasticity assumption. This is a good example of random scatter here. I don't see huge gaps or anything like that. And you may say, oh, there's a gap here and there's a gap here. Our sample size is really small here, right? And so this is a great example of seeing random scatter. It looks like my variance is pretty consistent across all of those variables, and I don't really see a pattern, right? And so I would say that all of these assumptions are satisfied because I see that random scatter. When checking the normality of residuals assumptions or assumption, this seems to be satisfied. I see that most of the points are close to that diagonal line. And so this assumption that the normality of the residuals is present, that is satisfied as well. And then if you were to look at the end of that table, in my final model, model M1, both of my values of my VIF for both of those variables were less than 10. And since they're both less than 10, I have satisfied that assumption. So all of the assumptions are satisfied. Now we're going to interpret the model summary table. All right. Our model summary table basically gives us our R-squared value. Remember, that was your coefficient of determination in simple linear regression. Well, we don't want to use the coefficient of determination, or R-squared, because it gets inflated by the number of predictors. And I'll show you here. Remember in that first model, we had 3 predictors. Notice that this R-squared here is larger. Because the more variables you add, the more variance you are going to explain, which makes sense, right? And so in addition to having this R-squared, this coefficient of determination, which we think is inflated because of the additional predictors, we need a method that can kind of offset the possible overestimation of the the variance that is explained by the model. And that is given by the adjusted R squared. It adjusts for the number of predictors to get rid of that overestimate of how much variable a model explains. So when we do multiple linear regression, we use the adjusted R squared. We do not use the regular R squared. The regular R squared is just the square of the correlation coefficient for simple linear regression. So this lies in simple linear regression. But this one we use for multiple linear regression. And so our value here is 0.689. And so we don't want to interpret it this way and say 72.1% of the variance in our outcome variable, which is heat cost, is explained by our two predictors in our final model, insolation and temperature. We don't want to do that because that is your coefficient of determination, R squared. What we do want to do is we want to interpret this 0.689. And so instead of 72.1, we'll say 68.9% of the variation in heat cost is explained by insolation and temperature. All right. So focus on the adjusted R squared. Now, there are times when we end up with a model with just one predictor. And I'll go ahead and say this. In that case, honestly, you can report either. If we end up with using multiple regression and you end up with one significant predictor in your final model, you can interpret your regular R squared. But some people, because you're using a model building method like the backward elimination, some people also like to report this to say, just so that people who's reading the report knows that a multiple regression method was used in order to end up with the final model that may have that has one significant predictor. So if we end up with multiple predictors in our final model, definitely use adjusted R squared. But if you end up with a simple linear regression model in your final model, what you can do is you can report your R squared and also report your adjusted R squared, because this is going to let them know that you probably explained that you use multiple regression in a certain model building process, but it adds validity to your results when you report that as well. All right. The next table was the ANOVA table. And basically what the ANOVA table is it's going through and conducting a global F test. Now, we talked about the global F test when we were dealing with the one-way and two-way ANOVA, right? Where we had the regression, the sum of squares between groups compared to the sum of squares within groups, right? And that gave us the components that led to our F statistic. Well, instead of thinking between groups and within groups, we're going to think regression and residual here. So this row here for that first model that had 3 predictors, this row is basically giving us the variance, a measure of the variability due to the regression equation, right? So how far off are those things from the regression equation and things of that nature? Variance due are explained by the regression model. That is given in this first row. Remember, if we do sum of squares divided by degrees of freedom, we get to the mean square. And then we get to the variance that is not explained by the regression, which is in this residual row. And so we get a measure of the variance there. Remember, sum of squares divided by degrees of freedom is your mean squares. And if we take the ratio of these mean square values, we get our F statistic. And that F statistic has 2 degrees of freedom, the degrees of freedom regression and the degrees of freedom error, residuals. And then we get our p-value from that F distribution. All right. So for each model, we get an F statistic and a p-value, right? And so basically in our model, we see that we have in our final model M1, we have an F statistic equal to 22.005. We have a degrees of freedom regression and a degrees of freedom residual here, 2 and 17. And we got a p-value less than 0.01. So this basically means that the model is statistically significant. Okay. And it basically indicates that there is at least one predictor in this model that explains a significant amount of variance in that outcome variable. So your model has some variables that is explaining a significant amount of the variance in your outcome variable. That is what this is doing. It's not telling me which variable, it's just telling me that I have a good model that's explaining enough variance in our outcome variable. Now we're going to be going to our coefficients table. This is where we get the actual coefficient values so that we can create our model equation. All right. Now, as I've already talked about before, the model building process concluded with 2 iterations. That's why we have M sub 0 and M sub 1, right? If we had 3 iterations, we would see an M sub 2. So our final model via backward elimination, it includes 2 significant predictors. Temperature, p-value is negative. Sorry, it's not negative. The p-value is less than 0.001. And then insulation, the p-value is 0.01. All right. This is from our coefficients table. Now, if we want to create an equation, we have a couple of options here. Notice we have unstandardized coefficients and standardized coefficients. So let's talk about the 2 different types of regression coefficients. Unstandardized coefficients represent the amount by which the dependent variable y changes when the predictor, that specific predictor x, increases by 1 while holding all of the other predictors constant, right? And so this is useful when we want to interpret the effect of our predictors in the units of our original data, right? So if I go back to this example here, notice this unstandardized coefficient or slope for temperature is negative 4.689. That means for every additional 1 degree Fahrenheit increase in temperature, we expect the heating cost to decrease by approximately $4.69 because our cost is in dollars, right? Holding insulation constant. So disregarding any values or differing values of insulation, right? We always add that extra caveat, holding the other predictors constant. If we wanted to interpret this regression coefficient for insulation, well, if we increase, so for every additional 1 inch increase in the number of inches of insulation a house has, the price or the cost of heating will decrease by $15.47 while holding temperature constant, right? So we got to ignore a whole temperature constant, but hey, we're seeing a decrease of $15 and about 50 cents, right? That's the interpretation using these unstandardized coefficients. All right, notice both of these are negative, which makes sense. If I increase the temperature in January or whenever that temperature was made, I expect my heating costs to decrease, right? And if I have more insulation to combat low temperatures or to keep stuff in the heat in my house instead of allowing it to escape, I should also see a decrease in my prices, all right, our heating cost. So that makes sense. But that's unstandardized coefficients. When we look at standardized coefficients, some people call these beta weights. They're expressed in standard deviation units, all right? So there's a way to standardize. So since our original variables are not in the same units, if we want to compare the importance of our predictors, which one has more of an effect on our outcome variable, then we're going to compare the beta weights, the absolute value of those beta weights. But they're created so that they're expressed in standard deviation units, and they indicate the number of standard deviations are dependent variable changes for 1 standard deviation increase in the specific predictor variable. while holding all of the other predictors constant. Okay, so we can write our multiple regression equation based on the output. And so we have our outcome variable, which is heating cost, equals our intercept plus a negative 4.689 times this variable, which is temperature. So instead of saying plus negative, I just said subtract or minus. And then plus another negative 15.466 times our insulation variable. All right, that is our equation. So if I have a temperature and an insulation number, then I can plug them into this equation and it can help me predict the heating cost. And that's something that I can use year after year. Or it may be something that I'll use in January and I'll use it for the rest of the season. Or me collect data and use it to make predictions later. All right, now that's using our unstandardized coefficients. I could write an equation using the standardized coefficients, but what we really want to do is see which of these variables is more impactful. And so I can look at the absolute value of these two standardized coefficients. And in absolute value, meaning ignoring the sign, the negative signs here, we can see that temperature has a larger absolute value standardized coefficient compared to insulation, which means temperature has more of an effect or is a more important predictor of heating costs compared to insulation. Now, if we were to just look at the absolute value of the regression coefficients that are unstandardized, it would look like the opposite scenario is happening. All right. And it's because these things are given in different units, right? And so temperature is more of a continuous variable. And so it changes, small changes can have larger impacts compared to insulation, which is a discrete variable. It's the number of inches. I think it's given as discrete, but if we think of length of the inches, then I guess I can say it's continuous as well. But in our measurement tools, it's probably going to be coming in the inches. And so a slight change here is not going to have as much of an impact compared to a slight change in temperature, right? So the standardized coefficient is bigger, which means it's bigger in absolute value, which means that this temperature is more of an important or has a greater impact on the heating cost. All right. So that's our regression equation. And so that is one example where we've gone through the full, all of the steps. I know that since we were going through those steps while also talking about some of the concepts behind it, let's go through one example, which is going to be more like what you'll see on a quiz or on an exam. It says a social researcher wants to examine how family income, family size, and the total years of education beyond high school for both parents predict the size of a home, which is measured in square footage. And so we're going to use backward elimination and a 0.05 significance level to determine which variables significantly predict the size of the home to be purchased. All right, size of the home is our outcome variable. All right, so I'm going to open up this data here. Let's give Jasper some time. Oh, I already got the variable. All right, yeah, we have square footage here, income, family size, and education, which is the number of years, right? Let's look back at the data just so that we can see. So square footage is given in these numbers here. Income is given in thousands. So this person makes 60,800, 68,400, so on and so forth. The size of the family. So there's two people in these homes, 3, 4. We got a family of 6, a family of 5. There's a variable in here that's called senior. It's an indicator variable, yes or no, indicating whether there's a senior in the home, senior citizen. And then education is the number of years beyond high school for both parents. So this is a very highly educated household here, where this household here has parents with only a high school diploma. But let's go ahead and run a linear regression. And so my outcome variable or my dependent variable is square foot or square feet. I have backward elimination here. I'm going to use income, size, and education as my covariates. I'm going to remember to go to method specification, change that value to 0.05, and I have my final model. If I look over here, I can see that I ran 3 iterations, so I have 3 separate models. My global F tests for each of those models are given here, and the p-values follow. And this tells me I started with my model with all 3 in there. Notice the first one that it eliminated after the first iteration was education. It was an insignificant predictor. My second model had both of these. Income was insignificant. And then I get to my third model where size or family size is the only significant predictor. So this is one of those cases where I have ended up with one predictor in my final equation. And so it says to use backward elimination. Well, based off of that, I have family size as my only significant predictor. And I can write my final regression equation. My intercept is 1271.586. And my slope for my size variable is 540.690. That means if I increase my family size by one individual, I expect the square footage of my home to increase by 540.69. All right. All right. So my regression equation is given here. Home square footage equals 1271.586 plus 540.690 times family size. All right. Using the results of the multiple regression, let's interpret the adjusted multiple coefficient of determination. So I asked here for the the adjusted multiple coefficient of determination is 80.2 or 0.802, as I saw here in this table. If I go to my model summary table to M2, my R squared is 0.824. That's for simple linear regression. Here, my adjusted R squared, which accommodates for the fact that I started with a more complex model, is 0.802. Again, in practice, you should report both, even in regression when you result in a single factor model, because this indicates that you started with a more complicated model. All right. So I can say that 80.2% of the variance in this predictor here, the variance in my dependent variable, home square footage, is explained by this predictor here, which is family size. And so in words, this is what I said. 80.2% of the total variation in house square footage is explained by the size of the family. Part C, are the assumptions met? So what I'm going to do is I'm going to go back to JASP here. I know I need my VIF, so I'm going to start here under the statistics, coefficients, VIF, intolerance. Look at the final model, and in my final model, my VIF is 1. That's less than 10. I'm good to go there. And since I don't have multiple predictors, I'm not going to have multicollinearity. So it's not possible. But I'll just go ahead and get into the habit of reporting that VIF there. And then the plots. Did I change this? Yes. Because this is one of the things that I always forget, sorry. Even your professor makes mistakes, of course, as you guys are well aware. All right, so I have my other 2 plots. You remember the residuals versus predicted. This is going to be used to check the linearity assumption, the independence of your errors or the independence of your residuals, and then also the homoscedasticity, right? And then the QQ plot is going to be checking the linearity, the normality of your residuals, right? And so I'm going to go and look at this plot here for all of the points except this point here. We're getting some random scatter. There's not a lot of data here. This is a very small data set. And so this point right here actually may be throwing me off because this creates a variance that is very high for values. If I look vertically, there's a lot of variability between all of those points. Whereas if I look at all of the other points, excluding that point, there seems to be random scatter. So I'm worried about this point here, right? There looks like random scatter in all of the points except for one. And since our data set is only 10, having this off point may be having a huge impact on the results and maybe making me not satisfy this assumption. All right. So while my VIF assumption is satisfied, my no multicollinearity, I'm worried about at least the linearity, homoscedasticity, and independence of errors here because of this one point. All right. When I look at my residuals versus my QQ plot of my standardized residuals, the points aren't too far off. Although these points here are leaning towards being a curve, but since it's not too far off, the points are not too far off from being close to that line, I'm not going to say that this assumption is violated. So I think my normality of my residuals assumption is not violated. My VIF, no multicollinearity assumption is not violated. I'm worried about the linearity, independence of errors, and homoscedasticity. All right. And so I've written this down here, and there we go. So what you're going to learn when you check assumptions in your next course is, one, sample size matters, right? Multiple regression requires usually a large sample size. And so your large sample size technique. If the sample size is small, then the assumptions need to be met very, very dramatically, right? And so that's one thing here. But here, my VIF is good. QQ plots shows points near the line. Residuals versus predicted shows random scatter, except for one point. This might be very impactful on my results. Further explanation is needed. So I would interpret these results or use the results that we've already come up with caution. All right. So I said that sample size is important for multiple regression because we usually need larger sample sizes. This sample size in this example is just 10. And also, when we have points that may be very, very big, so there's a point with a square footage. I'm going to go back and look at my data. I may not be able to tell it here which point is causing the problems. But I would want to explore this point right here. Because some points are so influential that they can impact the actual values of your coefficients so much that it'll throw your analysis off, right? And so there are some methods that you'll learn in your next course in order to find out if single observations are having huge impacts on the actual results. And so there's more to come on that later. For now, we're just giving an introduction to these assumptions. And so I think that's a good coverage there. For now, I think that is it for this video. If you have any questions, always reach out and let me know. Other than that, I'll see you. Well, this is our last video. So let me know if you have any questions. Bye-bye.